Hello everyone, in this tutorial we'll be going over how to do a Hyperloop simulation in OpenFOAM. Hyperloop is an idea for a public transportation system devised by Elon Musk, where you have a vehicle that holds passengers traveling through a depressurized tube. There's a technical white paper available on the SpaceX website that has some details of the preliminary design. And so here are the files for this tutorial case. We have the case, which is the OpenFOAM files, the mesh, which is a mesh written in Gmsh, and some post-process results, which I'll show at the end of the video. So first let's look at the mesh. Here we have a simple axisymmetric domain. This bottom line is this axis of symmetry, revolved about it, and this is the inlet, the outlet, and the actual vehicle here. So since this vehicle is moving through the tube, we have the vehicle set as a simple wall, and the top moving at the same speed as the airflow at the inlet, which in this case will be Mach 1. You can see that it's a wedge mesh here, as required by OpenFOAM. Alright, and we can take a look at the mesh generated in this case. So you can see I have some refinement near the vehicle to resolve the shocks that will form. You might want to add some boundary layer mesh if you wanted to capture some separation. So yeah. So let's go ahead and make the mesh here. We'll copy these commands found in the README. Alright, the mesh was generated. Now let's convert the mesh. Alright, now let's change the boundary file to be the appropriate boundary conditions. This is type wedge, as is the other wedge surface. Oops. And we have walls on the vehicle, and the tunnel, which is the top surface. Okay, now we're done with that. Now we can run the simulation. We'll be using the rhoCentralFoam solver. As you can see, it's running smoothly. In this particular case, we use a explicit method. So you can see there's a diagonal. It uses the so-called diagonal solver. So let's. It takes a while, so we can take a look at the post-process results. But first, I want to go over a little bit about the boundary conditions, which you can find in 0 here. We have boundary conditions for the velocity, temperature, and pressure. And you'll notice that these values are normalized. This simulation assumes an ideal gas. So these are normalized quantities, which works for any ambient conditions that you put in. You just use a multiplier on it. And is valid for when the fluid acts as an ideal gas. In this case, it would be. So here we have the velocity as a Mach number. We set it to 0.99, or basically 1 here. And the temperature as 1, the reference temperature. And in this particular example, we set the tunnel to have a fixed value and the vehicle to have a fixed value as well. The pressure is also relative. And yeah, so in the technical white paper on the Hyperloop, the pressure was specified to be 100 pascals, which is 1,000 times lower than atmospheric pressure. So even if we have shocks forming, the resulting drag would not be high. So let's take a look at the results. First, the pressure results. Here you can see the shocks advancing, and this is sort of an expansion here, where the flow is traveling faster. We are doing a laminar simulation here. We did not use a turbulence model. So you can see here there's some reflection of shocks off the walls, and basically, yeah, this tube has a bunch of shocks forming everywhere. In the so-called real Hyperloop, we have they use a compressor to reduce the drag, but also to generate pressurized jets for air skis, so that the vehicle can float, so to speak, within the tube. So here we have a closer look at the leading edge, and we can see the shocks forming more clearly. You see it advancing here, a sudden slowdown in the velocity. We can see the shocks being reflected, and then reflected back off, and just a bunch of reflected shocks here. Yeah. So that's all there is to it, to do a simple drag computation on a Hyperloop-like vehicle. Thanks for watching, and happy foaming.